So I'm a big proponent of loops in R. I think that's really where a lot of the power comes in. If you are an expert coder, there's usually simpler ways than looping things. I don't know if we really want to go over loops because I don't think they're going to be using these in our QTL or an MP map. But the idea behind a loop is we can cycle over some variable. And so just as an example here, we're going to say for I in 1 through 10. And then here's a curly bracket. And what we're doing is we're having it cycle over this code, changing I for each cycle. So the first time when we say test I is equal to 1. It's going to complete all the operations, and then it's going to start over, and I is going to be equal to 2. So it'll do that in a cycle. That's really useful for simulating something, and we're trying to do 1,000 simulations. You want it to repeat the same thing just over and over again. But in the software we're going to be using the rest of the week, they've built a lot of that into the code already. So you're not going to necessarily need to do that. And I'm more than happy to make these slides available to anybody who wants them. So you don't need to take notes. If statements. So one of the things that R is very powerful in too is logical arguments. So you can have it test things. This is really useful in the data manipulation side. So we can use logical operators like less than. We can ask the question, if this set of data is less than something, do something. Or if this set of data is less than or equal to, greater than or equal to, exactly equal to, not equal to, conditional. We can set up all these logical arguments in there to pull out just the data we want to analyze. And that's what makes it a really powerful tool. Because it does this computationally efficiently. Not as efficiently as C or C++ or something like that, but it's fairly computationally efficient and fairly easy to use. Now, input and output, this is going to be very different for RStudio. So hopefully somebody will interrupt me. But I'm going to talk about how we do this in R. Okay? And the way I do this in R is I set a path, and I call the path some root directory. And so in this case, it's my C drive, and then the class that I teach. Now note the slashes are actually opposite what it'll show you in Windows. So if I went to my folder here, and I wanted to paste in this, you see all these slashes are backslashes. So if I want to put this into R, I actually paste this in and then do a find and replace and change the backslashes to forward slashes. But once I have this path set up, that's sort of my working directory. And then I can paste a path that's concatenated. So this paste concatenates this function of the directory plus whatever I want to say. So let me just show you what this looks like. I'm not going to encourage you guys to do this because the path on your computer is probably complex and unique, seeing how these are university computers. So I just changed path to this function here. And now I'm going to add my matrix. I already have matrix 1 in. I'll do it again. And so if I wanted to write a file from some of the data we just did, it's not going to be able to find this. But what does this path look like? Copy this. What is our unexpected error here? Oh, this is something everybody should be aware of. If you're copying and pasting code in R, sometimes Microsoft's quotes are not the same as R's quotes. And so it gives you an error right away. It tells me, here's the error, and wherever it stops, that's where the error is. And for those of you in the back of the room, you probably can't see this, but those quotes are different than these quotes. And so it doesn't read those quotes the same way. So what I would do is I'd just hit the up button, and then I'd manually come in here and change the quotes to the type they're supposed to be. Okay, and so that paste function is concatenating this path here with this matrix1.csv to give it the exact file direction it needs. Now in RStudio, the cool thing you can do is you can set the working directory somewhere. Set working directory. So you can tell it where your source file location is. So since these are university computers, my guess is your source file location is whatever USB you plug into the side of this. So we can choose a directory. Maybe we can just choose it on the desktop. I don't know on these university computers. Yes, sir. Oh, you're talking about with R it works? Ah, okay. Ah, okay. I think I can just choose a directory here though, desktop, and I don't know. Path does not exist. Just send me a folder. Okay. So I have a working directory now, and I can probably save my whole R session into that. So for those of you who are interested in doing it, I'd just encourage you to Google it or look at a manual. Yes, sir. This is for RStudio or R? But how is that maybe I'm not understanding. How is that easier than just going to the set working directory and oh, okay. Okay. What did you say it was? Find what? Ah. Ah, okay. Be more convenient if you could just drag and drop it in there, wouldn't it? Yeah. Okay. So likely you would be having to input files for our QTL and export your output for our QTL. And so there's just some basic functions for doing that. But a lot of the data, I'm guessing that is going to be presented is going to be already in R. This was something that we were discussing the other day that could lead to some confusion. So when you load some of these packages, most of them have an example data set. An example data set that's built into R is, I think it's called htcars, for instance. Yeah, so you just type in iris, and here's an example data set then. Okay, so when you load some of these packages, there's already an example data set built in there. And so you can call that and take a look at it. One way that you can figure that out fairly quickly is, so I already loaded QTL in here. So I think I can just do this. I want QTL package. Is it RQTL? Thought I loaded it. You know what I'm really going to... Oh, there we go. So if we go to QTL here, and we click on this, the package information's here. And generally in the package information, it's going to tell you where the data set is. Example. What the data set is here. Example data hyper, based on hypertension in mouse. So if I type hyper, data hyper. There we go. Now it's loaded. Now if I type hyper in, there's the summary of the data. He gives you, tells too complex to print. So I think this is the example data that we'll probably start out with. That's my guess for our QTL for tomorrow. Okay, so the data is already loaded. But then we can also write CSV files. Generally, the input and output for our CSV files are one of the ones that in the past has always worked best for me. Can also deal with tab delimited. But generally, they're going to be some type of flat text file that you can open in Excel. You know, that leads a lot of people to confusion too. So let me see if I can write a CSV to the desktop. So I set my path already. So I'll try my write CSV. Oh, I don't know how to do that. The point I wanted to make is if you get a file that you write from RStudio or from R, you can right-click on it and hit Open With, and you can open it in Excel. Sometimes, especially if it's big, that's a little bit easier than other methods. So if I was to give you an example, you can just right-click on it and open with, and then go to Microsoft Excel if you get that output. But given the interest of time, we'll keep moving on here. We've already covered this, the different type of R data types. Missing data. So missing data is going to be a reality if you're using a real data set for any type of genomic data analysis. And one of the big problems is when you have that missing data, sometimes it changes the way that it views data. So the main type of data we're going to be interested in is numeric data, generally, right? We measure our traits. For instance, a plant height or an animal weight is a numeric type of data set. And we may sometimes have character data sets like naming the line. So this is recombinant inbred line 3. But what happens is when you have this missing data, sometimes it changes your vector or your array or data set into a character data set rather than a numeric data set, and then you can't do the analysis. So that's another thing that everybody needs to be very cognizant of and watch out for, is once you've input your data set, to take a look at it and make sure there's no NAs. Now, NAN is not a number, so I get those a lot when I try and do a calculation with something with either missing data or with a character. So we can deal with this a couple of ways. First of all, we can ask this question, is it an NA? And that's going to give you a true-false answer to tell you whether something you put in there is NA. So is dot NA X. So we've already used X. Is dot NA capital A. Okay, so all those things we generated in this AA value in the environment, those are all real numbers, so they are not NA. But now if we tried the same thing for hyper, for instance, which is data set, I would guess that some of that data is probably character data or missing. No missing data in the genotypes or phenotypes for that. If we signed anything a character, missing data. Well, it's something you can use for troubleshooting. Anybody else have comments on NA or missing data? I mean, generally it's one of those things that you have to troubleshoot once you have the problem. For me to tell you how to deal with it is a little hard until you see in what scenario you have that problem. But any other points people want to make? Okay. So I think we've accomplished the main objective so far, which is getting everybody logged into RStudio. Now everyone has a good appreciation for the fact that they need to get here on time to load RStudio and load the package. Otherwise, you're going to be playing catch-up the whole time. Hopefully you also got to play around with R a little bit, refresh your memory of what's important in R. The last thing I was going to go through real quick is just what is and isn't QTL mapping. I don't know how many people here don't have a solid background in QTL mapping, but I want to at least minimize that as a need to cover for tomorrow. And then we can go through that example data set. So a QTL, or quantitative trait locus, it's important to remember, is a statistical measurement. It is not necessarily a biological reality. Okay? So we're calling a QTL anything that's statistically significant and not necessarily a gene that affects a phenotype of interest, generally quantitatively, and it's going to have its boundaries defined by linked molecular markers. So what does that mean? Well, this right here is a linkage map. This is unfortunately in sorghum, I think. Remember, I'm just saying that because there's more sorghum people here than everybody else. So this is a linkage map in sorghum with the markers ordered along chromosomes here. And we can do some more complicated mapping, composite interval mapping, because we have an ordered genetic map with genetic distances. But we need to remember that QTL mapping did not start out this way. QTL mapping started with single marker analysis. And for the purposes of teaching QTL mapping, single marker analysis is still the easiest to teach. But in this case, we would have a QTL here, and the boundaries of the QTL based on your 1 LOD, 2 LOD interval would be physically defined based on the markers where we say they are no longer significant. And that would be our QTL. So the QTL in this case would be a region. If we're analyzing a single genetic marker, though, we may call that a QTL, even though we don't know what the flanking markers are. So what I want to do is run through some examples and some code to also point out the difference between significance and effect. Because remember, a QTL is a statistical measurement, not necessarily a biological one. And so in this case, we have little a, the mean of all the individuals with that marker is lower than the mean of all the individuals with the dominant A marker. And if you were running a SNP, you can just imagine These little a being a C, and this big A being G, for instance, homozygous, with a heterozygote in the middle. So we can look at the means of these various populations based on their classification of a single genetic marker, and we can do some type of statistical analysis on this. So we get an equation, and so what's the effect of this genetic marker? I'm sorry? Yeah, but it's actually right here. So what is here? I'll make the slide bigger. So what is the effect of that genetic marker? 5.2 per copy. So if you have 2x, it's going to be 10.4, right? So what type of inheritance is this? Additive, right? Because we believe that the heterozygote is in the midpoint, and we don't have a term for dominance in here. So this is just a simple additive model where each copy of the big A adds 5.2 to whatever trait we're looking at. So this tests for the effect. So that is the effect of the marker. This does not test for significance. Okay, so what I think I'd like everybody to run through is we're just going to do this this code. This will work. We can start with this. So while I'm talking, type in these things here. We're going to, oops, sorry. I'm going to generate. We're going to generate those random numbers. Big A is equal to our norm in parentheses 10, comma 110, comma 3, close parentheses. Big A, little a, or the heterozygote, is equal to our norm, parentheses 20, comma 105, comma 3, close parentheses. And then the recessive, little a, our norm, parentheses 10, comma 100, comma 3, close parentheses. So now you've generated random numbers with 3 different means. And what's the difference in the mean between big A, and little a? 10. And the heterozygote is 105. So this is an additive locus. And then there's a standard deviation of 3. Okay, and except these numbers are different. So then what I'm going to have you do is once you've gotten that done, just ignore these up here. Delete those. We'll do another term called big A-S, and that's going to be equal to the function cbind, parentheses big A, comma big A, comma little a, and close parentheses. So what does that look like for everybody? Remember, this is random number generation. So if you look at your buddy's computer, the absolute numbers will differ from computer to computer, or from run to run, I should say. Sir? Mm-hmm. Oh, that's helpful. Uh-huh. But only for that session of R. Like, if you do that and your neighbor does that, they're going to... Oh, will it? Okay. Mm-hmm. Sure. Cool. Sure. I'll have to incorporate that in the revision of this as you all give me feedback and tell me what will make a little more sense here. So if you ran this, you're going to see just genotypes with each of these, and you'll see that the means are different, as they should be. So all we did is we put those together.